Have you ever looked up at the night sky, filled with its countless stars and distant swirling galaxies? It's a breathtaking sight, a cosmic ocean of light and matter, stretching further than our minds can easily grasp. But what if I told you that everything you see, every star, every planet, every nebula glowing with brilliant color, is only a tiny fraction of what is actually out there? What if the vast majority of the universe is a ghost, a presence we can feel but cannot see? This is not a riddle from an ancient myth. It is one of the deepest and most profound questions in all of science. It is the story of a hidden universe, a secret power that holds everything together, yet remains completely invisible to our eyes and our instruments. This invisible substance has a name that sounds like it came from a science fiction story. We call it dark matter. It is not dark in the way a black hole is dark, absorbing all light. It is dark because it gives off no light at all. It does not reflect light, nor does it block it. It is utterly transparent, passing through the universe like a phantom. Imagine holding a pane of the purest, most perfect glass. Now imagine that glass had no weight, no substance you could touch, yet it had a powerful gravity all its own. This is the challenge that faces astronomers and physicists. They are hunting for something that makes up more than a quarter of our entire universe, yet it slips through our fingers and even our most powerful telescopes without a trace. The journey to understand this cosmic ghost is a detective story on the grandest scale imaginable. The clues are not fingerprints or forgotten letters. They are written in the movement of stars, the shapes of galaxies, and the very fabric of space-time itself. For decades, we have been gathering evidence, piece by piece, building a case for something we cannot directly observe. We are like detectives in a dark room, feeling the shape of the furniture, mapping out the space not by what we see, but by how it affects the things we can see. This quest challenges everything we thought we knew about the building blocks of reality. It forces us to ask, what is the universe truly made of? So, I invite you to join me on this journey. A journey into the shadows of the cosmos. We will explore the strange and powerful evidence that points to this unseen reality. We will look at the ingenious ways scientists are trying to catch a glimpse of this elusive particle, and we will ponder the incredible implications of what it would mean to finally unlock its secrets. Because understanding dark matter is more than just solving a puzzle. It is about understanding our own place in a universe that is far stranger, more mysterious, and more magnificent than we ever dared to imagine. The truth, as it often is hiding in plain sight, or rather, hiding in the dark. So what exactly is this mysterious stuff we call dark matter? The answer is both simple and deeply unsatisfying. We don't know. But we know what it is not. It is not the dust clouds that block starlight, creating dark patches in the Milky Way. Those clouds are made of ordinary matter, the same kind of atoms that make up you, me, and the stars. We can detect them with infrared telescopes. Dark matter is different. It's not made of protons, neutrons, or electrons. It doesn't interact with light or any other form of electromagnetic radiation. It is, for all intents and purposes, a new kind of matter, completely outside the standard model of particle physics that has so successfully described the world we know. Think of it this way. All the matter we have ever known, from the smallest ant to the largest star, is what we call baryonic matter. It's the stuff of the periodic table. This familiar matter accounts for less than 5% of the total mass and energy of the universe. The rest is a cosmic mystery. About 27% is dark matter. The remaining 68% is an even more bizarre substance called dark energy, a force driving the expansion of the universe. So the reality we experience, the world we can touch and see, is just the tip of a colossal cosmic iceberg. Dark matter is the immense hidden bulk beneath the surface, shaping the cosmos through its one known power, gravity. Its invisibility is its defining characteristic. Light particles, called photons, are the universe's messengers. They fly across the cosmos, carrying information about the stars they came from. When a photon hits an atom, it gets absorbed or scattered, which is how we see things. But photons fly right through dark matter as if it weren't there. Dark matter particles feel no electromagnetic force, no strong nuclear force, and no weak nuclear force. The only fundamental force they seem to respond to is gravity. This is why it's so hard to find. It's like trying to find a person who is invisible, silent, and can walk through walls, and the only way you know they're in the room is because they make the floorboards creak. This lack of interaction makes dark matter a true outsider to our known world. Scientists have proposed many candidates for what it could be. Perhaps it's made of particles called WIMPs, or weakly interacting massive particles. These are hypothetical particles that are heavy and interact only through gravity and the weak nuclear force. Or maybe it's something even stranger, like a particle called an axion, which is incredibly light. The search for these particles is one of the most exciting frontiers in physics today, because finding one would not only solve the mystery of dark matter, it would open a door to a whole new understanding of the fundamental laws of nature, a world beyond the matter we've always known. One of our first and most powerful clues for dark matter came from watching how galaxies spin. Imagine a spinning merry-go-round. The children near the center are moving slowly, while those on the outer edge have to move much faster to keep up. Now think of a galaxy as a giant cosmic merry-go-round made of stars. Our understanding of gravity, based on the visible matter we can see, tells us that the stars at the edge of a galaxy should be moving much more slowly than the stars near the center, where most of the mass, and thus the gravity, is concentrated. Just like the planets in our solar system, where distant Neptune plods along much more slowly than speedy Mercury. But when an astronomer named Vera Rubin pointed her telescopes at the Andromeda Galaxy in the 1970s, she found something that defied all expectations. The stars on the outer edges of the galaxy were moving just as fast as the stars closer to the center. This was a profound shock. It was like seeing the children on the edge of the merry-go-round spinning at a dizzying, impossible speed. A speed so fast they should have been flung off into the darkness of space. The only way this could be possible is if there was a huge amount of extra mass, and therefore extra gravity, holding those fast-moving stars in their orbits. Mass that we simply could not see. This discovery was not a fluke. Astronomer after astronomer looked at other galaxies, and they all found the same thing, a flat rotation curve. The stars at the edges were all moving too fast. The visible matter, the stars, gas, and dust, was not enough to explain the gravitational pull needed to keep these galaxies from flying apart. It was as if each galaxy was embedded in a vast invisible halo of some unknown substance. This unseen mass extends far beyond the shining spiral arms or the glowing core of the galaxy, providing the gravitational glue that holds the entire structure together. This was the moment dark matter went from a quirky idea to a necessary component of our universe. The discrepancy is not small. It's enormous. For a typical spiral galaxy, the amount of dark matter required to explain its rotation is about 5 to 10 times greater than the amount of all the visible matter combined. Think about that for a moment. For every star you see sparkling in a distant galaxy, there is a sea of invisible matter surrounding it, outweighing it many times over. The beautiful, shining cities of stars that we see are just luminous islands in a vast, dark ocean of gravity. Without this ocean, there would be no islands. The galaxies as we know them simply could not exist. They would have torn themselves to shreds long ago. If the spinning of galaxies scales. Knowing that dark matter exists is one thing. Finding out what it is, though, is another challenge entirely. Scientists around the world are engaged in a three-pronged hunt, a sort of cosmic search party, trying to corner this elusive phantom. The first approach is, well, to try and catch it right here on Earth. If dark matter is all around us, and it is, then billions of dark matter particles should be streaming through you, through the planet, and honestly, through everything on it every single second. The problem is, they almost never interact, but almost never isn't the same as never. Physicists believe that, very rarely, a dark matter particle might just bump into the nucleus of a regular atom. To catch this incredibly rare event, scientists have built some of the most sensitive detectors ever created. They place them deep underground, in old mines or beneath mountains, to shield them from all the other cosmic rays and radiation that constantly bombard the Earth's surface. These experiments are, honestly, marvels of engineering. One type uses large tanks filled with a liquid like xenon or argon, kept incredibly pure and cold. The tanks are lined with highly sensitive light detectors. If a dark matter particle, a WIMP for instance, happens to strike a xenon nucleus, it should produce a tiny flash of light and release a few electrons, a signal the detectors are waiting to see. So far they have seen nothing definitive, but with each new, more sensitive experiment, they narrow the hiding places for dark matter. The second strategy is to try and create dark matter ourselves. This is the work of giant particle accelerators, like the Large Hadron Collider at CERN. Here, scientists smash beams of protons together at nearly the speed of light, recreating the incredible energies that existed just moments after the Big Bang. The famous equation, E equals mc squared, tells us that energy can be converted into mass. The hope is that, in the debris of these violent collisions, new exotic particles will be formed, including particles of dark matter. We wouldn't see the dark matter particle itself, of course. Instead, we would look for its signature missing energy. Imagine you smash two cars together and all the pieces fly off. If you add up the energy of all the flying pieces, it should equal the energy of the collision. But what if it doesn't? What if some energy appears to have vanished? This could be a sign that an invisible, non-interacting particle, a dark matter particle, was created and flew away from the detectors without a trace, carrying that missing energy with it. It's another form of detective work, looking for what isn't there to deduce what must be. This search is really pushing the boundaries of what we can create and measure, taking us into a realm of physics beyond everything we currently know. Dark matter does more than just hold individual galaxies together. On the grandest of scales, it provides the very skeleton of the universe. Computer simulations of the cosmos have become incredibly powerful tools for understanding how everything we see came to be. When physicists run these simulations, they can input all the known laws of physics and the ingredients of the universe, including normal matter, dark energy, and crucially, dark matter. They then let the simulation evolve over billions of years, from the hot, dense state after the Big Bang to the present day. The results are nothing short of astonishing and reveal the profound importance of the unseen. What these simulations show is that very early in the universe's history, dark matter began to clump together under its own gravity. Because it doesn't interact with light or pressure, it could collapse into dense structures much earlier and more efficiently than normal matter could. Over cosmic time, these clumps of dark matter formed a vast, intricate network of filaments and halos, a bit like a three-dimensional spider's web stretching across the entire universe. This structure is known as the cosmic web. It is the invisible scaffolding upon which the visible universe was built. The bright, shining galaxies we see are not scattered randomly through space. They are built within this pre-existing dark matter framework. The normal matter, the gas that would eventually form stars and galaxies, was pulled by gravity into the densest parts of this dark matter web. It flowed along the filaments like water flowing through riverbeds, collecting in the deep gravitational wells created by the massive dark matter halos. It was in these pools of collected gas that the first stars ignited and the first galaxies were born. Without dark matter to provide this initial structure, the simulations show a very different universe. Normal matter alone would not have had enough gravitational pull to clump together so effectively. The universe would be a much more uniform, diffuse place, perhaps without any of the large, magnificent galaxies we see today. This idea is not just a theory from a computer. We can see the faint imprint of this cosmic web when we map the locations of thousands of galaxies in the sky. The Sloan Digital Sky Survey, for example, has created a three-dimensional map of the universe that clearly shows galaxies are not distributed evenly. They are arranged in long chains and great walls, surrounding vast empty voids. This large-scale structure of the universe is a perfect match for the cosmic web predicted by the dark matter simulations. It's as if we are seeing the glowing cities built along the invisible highways of the cosmos, providing yet another powerful piece of evidence that dark matter is the master architect of our universe. While the evidence for dark matter is overwhelming, the mystery is far from solved. In fact, the more we learn, the more questions seem to arise. One of the biggest puzzles is something called the cusp halo problem. Our computer simulations predict that the center of a dark matter halo should be very dense, with a sharp spike or cusp of dark matter right in the middle. However, when we observe actual galaxies, especially smaller dwarf galaxies, we don't see this cusp. Instead, their centers seem to have a much flatter, more constant density, a core. Why is there this mismatch between theory and observation? This discrepancy has led to some fascinating new ideas. Perhaps dark matter isn't as simple as we thought. Maybe it's not completely non-interacting. Some theories suggest that dark matter particles can interact with each other, just not with us. This self-interacting dark matter could bounce off itself in the dense galactic center, smoothing out the cusp and creating the core that we observe. This would mean dark matter has its own rich, hidden physics, a secret world of forces and interactions happening all around us. Another deep mystery is the sheer coincidence of it all. Why is there roughly 5 times more dark matter than normal matter in the universe? There is no known reason why these two completely different types of matter should exist in such a similar proportion. One is the basis for chemistry, life, and consciousness. The other is a transparent ghost. The fact that their amounts are within the same order of magnitude suggests there might be some deep, undiscovered connection between them. Some theories, known as asymmetric dark matter, propose that the abundance of dark matter and normal matter were set by a related process in the very early universe. And what if our entire approach is wrong? A minority of scientists wonder if dark matter is just a phantom, invented to save our theories of gravity. They propose that perhaps Einstein's and Newton's laws of gravity are not complete. Maybe gravity itself works differently on the vast scales of galaxies. This idea, known as modified Newtonian dynamics, or MUND, suggests that at very low accelerations, gravity is slightly stronger than we expect. This modification could explain the fast-spinning galaxies without needing any dark matter at all. While MOND has had some successes, it struggles to explain things like gravitational lensing and the structure of the cosmic web, where dark matter seems essential. The debate continues, pushing us to test the limits of our most fundamental laws. Imagine the day we finally find it. What would that moment mean for humanity, for our understanding of reality? The discovery of the dark matter particle would be more than just finding another piece of the cosmic puzzle. It would be a revolution in physics, on par with the discovery of the electron or the splitting of the atom. It would be the first concrete evidence of a world beyond the Standard Model, the theory that has guided particle physics for half a century. The Standard Model is a beautiful particle turns out to be an axion. It would solve another long-standing problem in particle physics known as the strong CP problem. The nature of the dark matter particle, its mass, and how it interacts would not just be a new entry in a textbook. It would be a guidepost, pointing the way towards a more complete, more fundamental theory of everything. The discovery could also open up entirely new technological frontiers, though likely not for a very long time. Think about the discovery of the electron. At the time, it was a tiny, curious particle. Nobody could have predicted that understanding it would lead to electricity, computers, and the entire digital world we live in today. In the same way, we cannot possibly foresee what harnessing the secrets of the dark sector might one day mean. Could we learn to interact with dark matter? Could its properties reveal new sources of energy or new ways to manipulate space-time? These are questions for science fiction today, but the history of science has shown us that yesterday's fiction can become tomorrow's reality. But perhaps the most significant impact would be on our perspective. For all of human history, we have looked out at the cosmos and believed that what we saw was all there was. The discovery of dark matter would confirm, once and for all, that we are living in a universe where the dominant form of matter is something we are not made of, something we cannot see, and something we do not understand. It would be a humbling and awe-inspiring realization. It would reinforce the idea that we are just beginning our journey of cosmic exploration, and that the universe holds secrets far deeper and more wondrous than we have ever known. The search for dark matter is a search for our true place in the cosmos. We began with a simple question: is what we see all there is? By now, the answer is clear. The universe we perceive with our senses is merely the shimmering surface of a much deeper reality. Beneath the brilliant light of stars and galaxies lies a vast, invisible architecture, a silent, powerful presence that has shaped the cosmos from its earliest moments. Dark matter is not just a missing piece of the puzzle. It is the puzzle's frame, the very thing that gives it its shape and structure. Without it, we would not be here. The galaxies would not exist. The cosmic web would have never formed. The universe would be a far less interesting place. This quest to understand the unseen has redefined what it means to be an explorer. The great explorers of the past set sail across unknown oceans to map new continents. Today's explorers build their ships from silicon and steel and sail them into the depths of the earth to listen for the faintest whispers from the dark universe. They build eyes of glass and mirrors that see not light, but the way gravity bends it. They are mapping a new kind of continent, one made not of rock and soil, but of a fundamental substance of reality that has remained hidden until now. Their journey is one of the greatest intellectual adventures humanity has ever undertaken. The story of dark matter is a profound lesson in humility. It reminds us that our perception of the world is limited, and that nature's imagination is far greater than our own. For centuries, we have built our understanding of the universe on the foundation of what we can see and touch. Now, we are learning that to truly comprehend reality, we must learn to appreciate the power of the unseen. We must be willing to accept that the most important characters in the cosmic drama might be the ones who never step into the spotlight. This is a shift in thinking that will echo through all of science for generations to come. So the next time you look up at the night sky, I want you to see it differently. Don't just see the points of light. See the immense invisible halos of gravity that cradle each and every one of them. See the great unseen filaments connecting them across the gulfs of space. See the hidden power that makes it all possible. The universe is not just what it appears to be. It is a grand cosmic duet between the light and the dark, the seen and the unseen. And we are just beginning to learn the music. The secrets of dark matter are waiting, and unlocking them will not just change our picture of the universe, it will change our picture of ourselves.